Buon pomeriggio a tutti, good afternoon everyone. Non so se ci siano persone che non parlano l'italiano presenti, ma ci è stato detto di fare la presentazione in inglese, quindi passo all'inglese. Good afternoon everyone, thank you for being here. I'm very pleased to introduce today's speaker in our colloquium of the Faculty of Science, Professor Umberto Bottazzini from the University of Milan. Umberto is a leading historian of mathematics at international level, certainly I would say the most eminent Italian scholar in the field. Umberto has had a very distinguished career, and I'm going to give you a brief summary. His degree is in mathematics, so he's a bona fide mathematician. Not all historians of mathematics are. He was associate professor for the history of mathematics from 1977 until 1990, first at the University of Calabria, then the University of Bologna, which is where I had the good fortune of meeting Umberto. Then he became, he also taught in the Department of Mathematics at the University of Pisa, briefly, in 1990, 1990. And then became a full professor, first at the University of Palermo, and then at the University of Milan. He also had positions at Sissa, Trieste, and Università San Raffaele in Milan. And since 2004, he is professor for the history of mathematics in the Department of Mathematics at the University of Milan. He's had a number of appointments as a visiting professor in France, Sweden, England, Belgium, MIT, and in many other places, including places in Italy like the Youth in Pavia. He also has been a corresponding member of the Académie Internationale d'Histoire des Sciences, member of scientific board of Centro Federico Enriquez. I'm giving you here only a short summary of the many activities of Umberto. He's won a number of recognitions for his work. For instance, in 2006, received the Pitagora Prize of the Città di Crotone for the best work in the popularization of mathematics. Most importantly, in 2013, he was elected a Fellow of the American Mathematical Society, of the inaugural class, in fact. And in 2015, Umberto won the Albert Leon Whiteman Memorial Prize, which is perhaps the most prestigious prize, one of the most prestigious prizes for historians of mathematics. And this is a prize also of the American Mathematical Society. He's organized a number of workshops in places like Cortona, Lumini, Centro de Giorgi. He's been numerous times invited to Oberwolfach and such venues. He's a member of way too many journals, editorial boards for me to mention. Most important, the Archive for the History of Exact Science and Historia Mathematica, of which he was also editor-in-chief. He has lectured widely around the world, including an invited 45-minute lecture at the International Congress of Mathematicians in Beijing in 2002. Umberto has written many articles, but is probably best known for his books, starting with Il Calcolo Sublime, Storia dell'Analisi Matematica da Euler Weierstrass, which was later translated by Springer, Flauto di Hilbert, and in general, numerous books on the history of what I would call modern mathematics, beginning in the late 18th century, but focusing especially on 19th century analysis, both real and complex analysis. More recently, he has published a couple of books on what we could call high-level popularization of mathematics with Il Mulino, Numeri, and Infinito. He's also a frequent contributor to cultural pages of newspapers. In particular, I was impressed to read that he's authored some 500 columns for the Inserto Domenicale del Sole 24 Ore, which is quite impressive. He's currently involved in the edition of the complete works of D'Alembert, in particular volume 4 on the vibrating string, and also the edition of the national edition of the works of Federico Enriquez. So Umberto has been a visitor in Pisa here before. He knows very well the archives here, especially Betti's correspondence. I want to add a personal note. In 1986, 1987, I had the good luck of being following his lectures in Bologna on the history of mathematics, and I kept the notes to these days. So, without further ado, Umberto, please.
Thanks. That's the weakness of the age. So, thank you, Michele, for this very nice and very kind presentation. I'm very honored to be here, and probably I have to read this. Sorry. Yeah. Start again, or no? And yeah. So the subject of my talk is not the sea, but is the infinite in a various way of understanding it. The sea is a sort of metaphor suggested by various authors. To begin with, there is a nice sentence by Nietzsche taken from the Joyful Wisdom, where he said, forget the last line, that nothing is more frightful than infinity. So the idea is that infinity is a frightful concept, and the idea that the ocean is so a terrific image for that. It's not Nietzsche, but only Nietzsche, but also many authors in the time have used this metaphor, like Bonaventura Cavalieri. And then at that time, this was suggested, I think, by the great navigators who sailed the ocean to explore the new continents. And Cavalieri, for instance, after receiving Galileo discorsi, say new sciences, discourses and mathematical demonstrations, has his master saying that with the spirit of your supreme genius, you succeeded in easily sailing the immense ocean of the indivisible, the vacuum and the infinite. And also, speaking of himself, he said that he was able to read the heaven, to the heaven, the boat, not that Nietzsche's, but his own boat, that has traveled the ocean of the infinity, of the indivisibles, avoiding to crashing on the rocks of that infinity. Another author who is interesting in this respect is Fontenelle. Fontenelle was secrétaire perpétuel of the French Academy for some 40 years or so. He died when he was almost 100. And in 1727, he published a book anonymously, but everybody knew that was Fontenelle, the author, on the elements of geometry. And that is an interesting book, because it got a number of reactions, including that from from Leibniz, and later on from Cantor and Veronese and others. But at that time, Fontenelle wrote that there is two kinds of infinites. One is the metaphysical one, a magnitude without limits in all the senses, which includes everything and out of which there is nothing. And then there is what he called the geometrical infinite. That means a magnitude greater than any finite magnitude, but not greater than any magnitude. And so the conclusion in this way, in his eyes, is that there are infinities smaller or greater than other. And look at the first instance he says that geometrical infinity gives rise to the incommensurable, whose number is infinitely greater than the commensurable. So apparently, what does it mean? That the irrational numbers are infinitely many more than the rationals? Proving that was one of the great results by Cantor. So apparently, Fontenelle had this kind of, I would say, insight or intuition or whatever. And then there is a nice picture provided by him when he says, it is said that in the Netherlands, large expanses of land have been covered by the sea, and only the tips of the bell tower emerge or scattered here and there. And it's more or less like this, that in the ocean of the infinity has submerged all the numbers and all the magnitudes, and only the commensurable can emerge, or you can perfectly know. So the rational number emerged in the sea of the continuum, the sea of the number, the rational number. Fontenelle was a very peculiar character, and it is nice to read what Leibniz said of him when Leibniz, realized that Fontenelle wanted to write a book like The Element of Geometry. So Leibniz was not very, I say, enthusiastic or happy about this project, because he was not very confident in Fontenelle's quality as a mathematician. But that is another story. So because we thought of irrational, one could say that the discovery of irrational number was someone has said, the first crisis in the history of mathematics. I just take a picture of the regular pentagon, because it's one of the first example of irrational ratio. That means that the ratio between the diagonal and the side of the pentagon is given by the golden ratio. That is an irrational number. But it's also interesting because this picture has a story, as represented on the right by this imaging from De Occulta Philosophia from Cornelius Agrippa's, and everybody can recognize the first instance of Leonardo's what is called Vitruvius Man, and 1 euro as this on the by Leonardo, not by Agrippa. Anyway, I'm interested in this because there is recently has been published a correspondence between Andre Weil and his sister Simone, and this is quite interesting in this respect, concerning in many respects, but in this part in particular, concerning the irrational number. So let me quote what André wrote. At that time he was in jail in Rouen, because it was at the beginning, in 1940, France was in war. He came from Norway, so and at that time he was waiting for the trial. And so he wrote to his sister, the fact that there are ratios that cannot be named, and for the Pythagoreans, a name ratio is between two whole numbers. That means that there have been logoi alogoi, and the expression itself is so overwhelming that I can't believe that in such a so dramatic era, which has known and felt anguish to such an extent, a fact so extraordinary could have been taken for a simple scientific discovery. That is André, and the reply no, sorry, again, André to Simon, he said that the great importance attributed to the proportion suggests that at the beginning of Greek thought, there was a feeling of disproportion between thought and word, and addressing his sister, as you say, between human and God, of such an intensity that they had need to throw, and it cost a bridge above that abyss. And Nietzsche, that is because I've mentioned Nietzsche at the beginning, Nietzsche meditated more than anyone else on archaic Greek thoughts. That is nice, Simone. I can't stand Nietzsche. He exasperated me, even when he expressed a thing, I think. That is okay. That is interesting. I will suggest you to meditate on this statement by André. He says that what makes Greek mathematics extremely original is perhaps the fact that approximation does not exist. Approximation does not exist. This killed the number for the benefit of logos, and that is the drama of the discovery of the irrational. Quite recently, a colleague of mine, or of us, I would say, that Paolo Zellini has published a number of books on this subject, and is claiming exactly the contrary, that the beginning of all that is like just approximation, not the approximation does not exist, as André Weil claimed at that time. Anyway, sure, says Raymond, there was a drama of immense scope, and the disclosure of the discovery of the irrationals has thrown on the notion of truth a discredit that still lasts nowadays. And it reached a progress that ended up destroying Hellenic civilization, and with the Roman weapons finally killing Greece. And the conclusion is that God have been right to let Hippasus of Metapontum perish in a shipwreck because of this, because he, as you know, was responsible, according to the Jamblichus, that to let known that the irrational has been discovered in the Pythagorean circle. To characterize the irrational numbers or the incommensurable magnitudes, Euclid uses what is called the antipharaesis. It's an algorithm of repeated subtraction applied to homogeneous quantities. And in Book 2, one of the arithmetic books of the elements, Euclid states that, you see, when the less of two unequal magnitudes are continually subtracted in turn from the greater, that which is left never measure the one before it, so the first one. That means that the magnitudes will be incommensurable. So let's shortly look at the infinite in the Antiquity. For Anaximander and for all the pre-Socratic philosopher of nature, infinite has taken the form of the apeiron, this indefinite, the unbounded, a kind of principle, says Aristotle, who says it's difficult, raises difficult in everyone, and the question is, where does the belief that there is something infinite comes from? An answer by Aristotle is that time is in fact infinite. That is a quite crude, I would say, statement, and not proven by Aristotle anymore. And then from the division of the magnitude as used by the mathematician. However, you know, infinite as such can be known, and we must not believe in an infinite that can exist actually. So all that remains is to conclude that exists potentially. And this kind of distinction was accepted and repeated for centuries. Anaxagoras says that in the small there is no small, and that means that you can continue the division as far as you want. Accordingly, the continuum cannot be put together out of discrete elements. And that is an important question, because one of the main questions discussed from the Antiquity until yesterday is how is made up das continuum, or the continuums. The infinite show up itself first in the continuum, say Aristotle. That is because infinite is often used in definition of continuous. For instance, that is infinitely divisible is continuous. And that means that if you, as Aristotle does, think that a point is an indivisible with position, that implies that the straight line is not made by points. A collection of points, however large, cannot give rise to something divisible like a line. And according to Aristotle, the straight line is continuous and the point is indivisible. Therefore, it's impossible that something continuous is composed by indivisible. And this thesis was repeated many times. For instance, by Roger Bacon, and his Opus Maius stated that any body is infinitely divisible, yet it is not for this reason that the world will be composed by infinite material parts, called atoms. And the example he provides is the following. Suppose that this is true. So consider a square and a diagonal, and then send the line parallel to the basis. So you put a one-to-one correspondence between the side and the diagonal. And this establishes a correspondence that is a point-to-point correspondence, and the conclusion is that the side and the diagonal are equal. And if a doctor mirabilis Bacon argues this way, so the doctor subtilis cannot do certainly be outdone. And so even Duns Scotus provides a similar example with two circles instead of a square, with two circle and the rays coming out from the common center. And later in 17th century, Libertus Fromondus from Louvain, was a mathematician and theologian, addressed philosopher, mathematician, and so on to fight atomism. And one of the arguments was that if space and time were composed of extended divisibles, not even a winged horse could reach the tortoise that has a certain advantage. And this is one of the Zeno paradox. The first one is the paradox of the arrow. Yeah, everybody knows, I think, no, the arrow cannot reach the target. And so if you're supposed to have a mobile point, it cannot travel from a point A to a point B of a line, because before it should reach the middle, and so on and so forth. How to solve this kind of paradoxes? According to Aristotle, the solution, the Achilles is the same. The solution is provided by a definition of the infinite in two meanings. One is infinite by division, the other one is by extremis, that means by length. In the second meaning, it is certainly impossible to touch the various points in a finite time. Instead, it's possible if the infinitives are thought of as according to the division, because in that case, also the time is infinite in the same way. So the conclusion by Aristotle is that it's not absurd that in infinite time we travel along infinite elements of points. As Borges says, ignorant people suppose that infinite draws require infinite time. The Lottery of Babylon is the novel. It's enough, in fact, that time is infinitely divisible, as the famous parable of the race with the turtle teaches. Achilles the same. Assume that tortoise has a head start of length 1 on Achilles, who runs twice as fast as the tortoise. So you get this geometric series converging to 2. And according to Weil, this could be a hint by which today one might think to resolve the paradox. One might think to. But Achilles exhausting all the infinitely many partial distance, as chopped off walls, is contrary to the essence of infinity as unfinishable. And Hermann Weiss, and not Andre Weil, Hermann Weiss goes on discussing the idea of continuum that Aristotle had. According to Aristotle, when you divide a continuous line, a segment, say, in 2 halves, you take the one dividing point for 2. You make it both the beginning and the end. And in doing this, in dividing in this way, neither the line nor the motion remains continuous. The motion of the Achilles, for instance, remains continuous. Of course, you have to think in not in actual term, but in potential term. On the contrary, everybody knows in this room that according to Dedekind, the statement that there is only one point which divides a segment into 2 parts is an axiom that characterizes, according to Dedekind, the essence of the continuity and allows him to prove the equivalence between arithmetic and geometric continuum. So that is, I will come back on this later, mention again what Hermann Weil says in this respect. As for the composition of the continuum, not only Aristotle but Hegel says that a sum of points does not produce a line. The reason is that if you think the line as a set, a Menge, says Hegel, of points, the continuum is reduced to discrete. So it's impossible that Menge is, of course, the word used by Cantor. It's impossible that a continuum be made of points. And Paul Dubois-Reymond repeated the same, argued that in a static conception of space, like that of Dedekind and Cantor, a static conception of space cannot generate the notion of uniform line as defined rigorously by a however dense sequence of points. Why? Since all the points have no dimension, and therefore, however dense it may be, the sequence of points can never become an interval, which must always be considered as the sum of interval. So the continuous line is the sum of continuous interval, and not of point. This kind of argument is taken, was repeated if you want, by Kant in the proof of the antithesis of the second antinomy of the reason, and is also taken up by Veronese in the foundation of geometry. He claims that the point is not part of a continuous straight line, and that all the points that can be imagined in it, however many they are, taken together do not constitute a continuous. That's Veronese, something more than 1 century ago, but after all that comes back from Aristotle. Since a point cannot be continuous with a point, he denied that a line can be composed of points. And make a suggestion of a comparison with time. A point is like now, or the instant, is an indivisible in time, not a part of the time. An instant can be the beginning, the end of the division of time. And similarly, a point can be the beginning, the end, or the division of a line, but not part of it. Almost the same words are mentioned by Laplace in his Leçons de mathématiques à l'école normale. Come back to Hermann Weyl. In 1927, he claimed that the continuum, or the variable, is represented by a sequence of choice in becoming, created step by step by unconditional choices that are independent of one another. Don't ask me what does it mean, but therefore, according to Weyl, remains in statu nascenti, while a sequence given ad infinitum by a law represents a single real number belonging to the continuum. Weyl, this is a paper on the philosophy of mathematics, Philosophie der Mathematik in 1927, and in that paper Weyl stated that according to Brouwer, the continuum is not composed of parts, like Aristotle. Weyl added that in the intuition conception, find a precise mathematical formulation and all the truth expressed by Aristotle. So you see, it's not so far away. Because we think, we speak of continuum, and Aristotle, let me mention in passing a very well-known example, Aristotle Wheels, discussed by Galileo. You see, the question is, how can the smaller circle running along the line BF, traverse a length greater than its circumference, unless it go by jumps? And Sagredo say that's a very difficult question, very intricate matter. So the answer by Galileo is that there is a sort of look at the hexagon over there. You see there are dotted lines and continuous line. If you think of a circle as a polygon having an infinitude of sides, the line traversed by the continuous distributed infinitude of sides in the greater circle equal the line laid down by the infinitude of sides in the smaller, with the exception of an infinitely many empty spaces, just like in the example of the hexagon. And since the sides are not finite in number but infinite, so the empty spaces are not finite but infinite. And simply just says this building up of lines out of points, divisible out of indivisible, infinite out of infinities, offers me an obstacle difficult to avoid. Not to mention the vacuum, conclusively refuted by Aristotle. And so Salviati said, remember that we are dealing with the infinities that both the indivisible, that both transcend our understanding. And then there is the example of the ball, is another fantasy of paradoxical nature produced by Galileo in that book. The question is, how can a single point be equal to a line? Shortly, imagine to rotate this figure around CF, so you get a cylinder, a cone, and a sphere, and then take up the sphere, and so what remains is the ball. And I cut this with planes parallelly to the basis, and so you get that figure, and the section shows that they are equal, the section of the cone and the section of the ball, and then suppose to have your cutting plane coming near and near to the top, and so in the end you get a point, that is the vertex V, and a line, that is the circle. As they are still equal, in the end they should be equal. And Sagredo says, to deface so beautiful a structure by a blunt pedantic attack would be nothing short of sinful. And who is making a blunt pedantic attack? This is Cavalieri. Cavalieri say, if you look at this picture, in the end, there is no plane and there is no section, and the fact that on one side you have a circumference and the other side a point has nothing to do, because it is no plane, the line, as much as the point. So this is a question very interesting because it involves the so-called law of continuity. Is the behavior of a sequence of continuous functions continuous in the limits? This is the source of one of the mistakes, entre guillemets, by Cauchy, for instance. One other interesting question is the following, arises by Simplicius. Since it's clear that we may have a straight line greater than another, each containing an infinite number of points, we are forced to think or to admit that we have two or many different kinds of infinity, one greater than the other, because the infinity of points in the long linear is greater than the infinity of points in the shorter. That is a difficult arising, but with our finite mind try to discuss the infinite, yes. Then there is the example I don't mention because everybody knows that, the number and the square. But what to conclude? The conclusion of Galileo is that the attribute equal, greater, and less are not applicable to infinite, but only to infinite quantity. And again, answering to example by Simplicio, I answer that one line does not, you have different segments, shorter and longer. One line does not contain more or less or just as many points as another, but that each line contains an infinite number. Yeah, one would say infinitely many, that's sure, but as many, not as many in the sense of Cantor. And Galileo said, no, it's not the case. Again, there is an answer by Galileo to Rocco. I would recommend to look at this paper by Galileo. It's amusing, actually. Rocco claims that it's false thinking of a line made up by points, and so it's false that a sphere is tangent to a plane at a point. Why? because it would follow, against Aristotle, that a line is composed of points. Galileo answered that it's true that continuous consists of always divisible parts, and so it's very true that the line is composed of points and the continuum of indivisible. Open your eyes and look. Open your eyes at the light that has perhaps concealed so far, and you will clearly see that the continuum is made up divisible. Okay, these indivisible are not quanta, to use Galileo term, for if they are infinitely many, quanta would compose an infinite quantum, a big one, of course, and not... It's interesting to remark that this is not just a question of mathematics, a matter of mathematics, it's a matter of theology. And the Jesuits declared that the continuous composite of indivisible is not only in contrast with the common Aristotelian doctrine, but also improbable in itself, and therefore forbidden in our company. And in 1651, among the philosophical theses that were condemned, there was statement like the continuous of sequence consists only of indivisible, or the infinite can be enclosed between two units or 2 points. That is what Galileo said, for instance. And not only the Jesuit, but also Spinoza, in the Ethics, mentioned the fact that there are some who pretend that the line is made up of points, and then they are good at finding arguments to show that it can not be divided infinitely, and in fact is not absurd to argue that the body substance is made up of parts, and the body is made up of surfaces, and surfaces of line, and line of points. All that is absurd according to Spinoza. And the infinites appear also when we look outside the mathematics and look on the sky, and one of the discussion arose in 1606 when a new star appeared in the sky, and Kepler, commenting on this, and this De Stella Nova, reacted sarcastically against the sect of philosophers who come from the ancient school of pagan philosopher and are lost, in his view, in inexplicable labyrinths, as happened to the unfortunate Giordano Bruno, who makes the word infinity in such a way that how many are the fixed stars, so many are the worlds. That was Bruno's. And in this respect, Kepler said that thinking of this, wandering in this immensity, provoked to him a kind of horror. How is it possible that the universe is infinite? Asked Elpino to Filoteo in the Dialogo, the infinite universe mondi by Bruno. And I asked him, how is it possible that it is finite? You cannot prove with the senses. You cannot prove with the senses you have a notion of infinite. And Filoteo, that is Bruno, claims that the immense space that we can call vacuums, in which there are innumerable and infinite globes like this one, like the Earth, and this, with this kind of infinite, there is no reason that should be finite. And in his view, all these would celebrate God greatness by countless suns and infinite worlds. But unfortunately, the fathers of the Inquisition did not agree with that. Calvino said that Bruno was a great visionary, cosmologist. And in Borges' opinions, Bruno proclaimed that this was a statement repeated many times at that time. We can say that with certainty that the universe is all center, or that the center of the universe is everywhere, and its circumference is nowhere. And that is taken by a Liber Philosophorum, an hermetic test. Contrary to that, Kepler claimed that the universe has a finite spherical shape because it's the bodily image of God. Mundus est imago Dei corporea. What say Galileo? He said he was not able to support the finiteness of the universe, and in the Dialogo said, Salviati, as Galileo says, neither you, Simplicio, nor anybody else has ever proved that the world is finite and endowed with any figure, or infinite and unending, or unending. Unending as Leopard is space in the infinite. Pascal also repeats what Bruno, the heretic Bruno, says, that the space is an infinite sphere whose center is everywhere and circumference is nowhere. And Leibniz said, look, this kind of expression should not be taken strictly because they are somehow like the imaginary, not rigorous, but useful. And Pascal not only is terrified by the infinite spaces, but the eternal silence. Is terrified. All that terrifies me, say Pascal. And that's interesting, the comment by Borges. Pascal works reflect for us the vertigo of a theologian exiled from the orb of the Almagest and lost in the Copernican universe of Kepler and Bruno. As I mentioned Leopardi, so he asked, the infinite is an idea, a dream, and not a reality. We have no proof of its existence, not even by analogy. We can say that we are at an infinite distance from cognition and demonstration of such an existence. Indeed, that's interesting, is written about in the 20s. It could be somehow disputed if the infinite is possible, something that some moderns have denied, and if this idea, daughter of our imagination, is not contradictory in itself, that is, false in metaphysics. At that time, more or less at that time, Bolzano was thinking of the paradoxes of infinite and emphasized the properties that we have seen was discussed by Simplicio and Galileo. That is, the property that infinite sets, would say, can be put in one-to-one correspondence to each other. There is a high remarkable peculiarity which can occur and actually occurs in the relationship of two multitudes if they are both infinite. It's possible that one of these multitudes contains the other in itself as a mere part. So that is exactly what Dedekind would say in his book on the nature and meaning of numbers. when by definition a system, a set, say, is said be infinite. When it's similar, that means in one-to-one correspondence to a proper part of itself. So if you want the infinite in some way precede ontologically the finite. And let me just mention in passing this. I already mentioned Dedekind, his axiom, but at that time when he wrote the paper on continuity and irrational number, he got in touch with Cantor, and Cantor in his letter asked this kind of question to his friend. Is it possible to establish a one-to-one correspondence between real numbers and natural numbers? Some time later, he was able to say no, and then I found a clear difference between the so-called continuum and the set of all algebraic numbers. Actually, more correctly, Dedekind found a clear difference, and Cantor published it as his own discovery, but that's another story. The set of algebraic number is the number of the real number is not, as the power of continuous, and in a paper published in 1882, he said that it occurs often that the concept of potential and actual infinity get confused. And so there are two forms of actual infinity, namely the transfinite and the absolute. The transfinite is that of interest of Cantor. And the question is, does a transfinite cardinal number between the power and, so that means rational, say, number and the continuum exist? As you know, that is an hypothesis with which Cantor tried for many years to prove, but in the end was unable. Although he stated he had proved it, but it was not true. So the hypothesis is that the power of the continuum immediately follows the power of the enumerable. And so I will mention this as the problem, the first problem actually, of celebrated talk by Hilbert, that every system of infinitely many real numbers is either equivalent to the assemblage, the set of the natural integrals, or the set of all real numbers, and therefore to the continuum. That is to the points of the line. So you see, the story, which began with Aristotle and so on and so forth, arrived to this point, but this is the beginning of another story, because from here onwards, the question, the continuous hypothesis and so on and so forth, is a topic discussed by set theorists, logicians, and so on and so forth. But I will stop here. Thank you very much.
Thank you, Umberto, for the very interesting presentation. I'm opening the floor for questions or comments. Well, I'll ask a question.
Okay.
I was curious by the opening statement when you quoted Andre Weil said that what was so original in Greek mathematics was that there was no approximation, and that indeed that seems to contradict, for instance, much of Archimedes' work. Do you want to comment on that?
Yes and no. That means, yeah, one could say, okay, Archimedes comes later, very later, with respect to the discovery of the irrational number. And so it seems that could be an answer, but in fact it's not, because it's true that Archimedes provide approximation of pi, for instance. So I don't know what Andre Weil meant by saying that in the Greek thought there is no approximation. I would say I disagree, but as is Andre Weil, so I'm slightly hesitating to say. So it seems to me instead that we have many instances of approximation of square root of 2, for instance, in ancient culture, not in Greek, or not only in Greek culture, but in Babylonian culture, for instance, or in Indian culture and so on, in Egyptian culture. So it seems that the approximation of a rational number like square root of 2 was sort of common achievement by different mathematical culture.
Ci sono altre domande? No? Bene, allora ringraziamo di nuovo.
Thanks. Thanks.